Now we're moving on to initial value problems. And a initial value problem, I guess we should define before we start. So an initial value problem is a differential equation with an initial condition. We'll see them a whole lot in this class, and so here's one right now. Du dx minus 3u equal to 0. That's the differential equation that we talked about in the introduction to differential equations. And then its initial condition could just be u of 0 equal to 7. And here we're saying that x would be something that, oops, don't need that, sort of goes like that. It starts at 0, and we would want to solve it starting from that initial point, x equals 0. And maybe what would help is to sort of better understand why we consider initial value problems. So a differential equation is a rule that describes the behavior of your dependent variable. So differential equations are how we describe like physical rules, like the tendency of cold things to become warmer when exposed to heat, or the tendency of falling objects to head towards the ground because of gravity. Those are things that are described by differential equations. They describe behaviors, something that we call dynamics. And those rules are helpful, but in order for them to have physical meaning, you need to know where they happen. You need to know what temperature something was before it started warming up to know what it means for it to become warmer. You need to know how high something was before it fell for its travel towards the ground to be meaningful. So initial conditions sort of ground us by giving us the starting point or giving us the location for the behavior. And I'll go ahead and write those examples out in words real quick. So Newton's law of cooling is an ODE. My coffee was hot when I started these videos. And now it is not. So I guess a solution to the ODE would tell me my coffee is currently cold. If you're more of like a graphical thinker, you could sort of say, I need to draw this a little bit. Oops, ran out of room because I am not a very graphical thinker. So a rule would be follow dashed lines. but a solution could end up at any of these positions because they're all attached to dashed lines. And it depends on where you started. So if I started right here, I would, hop to that purple star. But if I started right here, I would pop to that purple star. And that's the initial condition. So that's why this idea matters, because initial conditions tell you where your differential equation behavior starts, so it affects where you end. And so our goal with initial conditions are going to kind of break up into two different parts. So in general, what we're going to want to do is we want to find a unique solution to a given differential equation that satisfies an initial condition. And what we're going to go ahead and do right now is just look at sort of the algebraic mechanics of what that means. And then afterwards, we'll talk about something a little bit more theoretical about some pitfalls we need to look out for. So what's going to happen is, actually, this will be easiest with an example. So for example, let's look at this differential equation. Du dx minus 3 times u is equal to 0. That's the same as that du dx equal 3u that I've been talking about all along. And we're going to go ahead and have an initial condition. We'll say that u of 0 is equal to 7. That's our initial value problem. And what I'm going to say right now is that u equal to c e to the 3x is a solution to the differential equation du dx minus 3u is equal to 0. And so we'll learn throughout class how to find that sort of thing. Most of class will concern this little arrow right here. Given a differential equation, what kinds of solutions does it have? But for this brief introduction to initial value problems, I'm just going to give that to you. So we found types of solutions, but really what we want is the unique solution that satisfies the initial condition. So if we want to satisfy the initial condition, we need u of 0 equal to 7, or c e to the 3 times 0 equal to 7. Because I said that this is what u is. U is c e to the 3x. When I plug in x equals 0, I get c e to the 3 times 0, and it should be equal to 7. But e to the 3 times 0 is e to the 0. That's just 1. So what I have is c equals 7. What I did was I just solved for c. And so the unique solution, well, we'll talk about uniqueness later. The solution to the initial value problem is u equal to 7 e to the 3x. Oops. Okay, we're just going to not close that box. And so you'll get a little bit of practice with this when you do your web work, you'll see given a differential equation and the solution, just plug it into the initial condition, solve for unknown constants. I'm going to stop right here, and in the next set of videos, we'll delve more into that theoretical stuff that I think is going to be a little bit tricky in this section.